In this video, we are going to continue our review of Calculus 2. And in the previous video, we focused on reviewing the concepts and the ideas and the notation around integrals and Riemann sums, and some of the more obscure ways that integrals and Riemann sums can be calculated or estimated, for example, from tables or from graphs. In this video, we are going to review the more common or traditional way of calculating the value of an integral, which is to use what are called antiderivatives and to use what is called the fundamental theorem of calculus. So to remember what the fundamental theorem of calculus says, it says that if you have two functions, one of them called capital F, one of them called lowercase f, and you have capital F, which is an antiderivative of lowercase f, then the integral of lowercase f can be found by taking capital F, plugging in the two limits of integration, and then subtracting. So this can give us a very, very efficient way to calculate derivatives, but generally speaking, the most challenging part of using this theorem is finding this function capital F, which is the antiderivative of lowercase f. And there were all kinds of different formulas and techniques and tricks that you learned in Calculus 2 to find this particular function. But even with all of those techniques and tricks, there are still many, many functions for which an antiderivative cannot be found, or an antiderivative is simply very hard to find, in which case a Riemann sum estimate is generally better. Now, as we were reviewing Calculus 1, we noted that there were a couple of different basic toolkit functions, and those were the functions from which all other functions were created. The basic toolkit functions were things like x to the power n, e to the x, natural log of x, cosine of x, and sine of x. And by combining these toolkit functions in various ways, either through addition or subtraction or constant multiples, multiplication, division, composition, inverse, etc., you could create pretty much any other function you wanted by combining these basic five. And so if we know the derivative rules for these basic five functions, then we can calculate derivatives for a large variety of other functions. And the same thing is true for integrals. It's very, very important for us to memorize the antiderivative formulas for these five basic functions, because those are the building blocks for the antiderivatives of all other functions. So for x to the power n, the antiderivative is found by increasing the exponent by 1 unit and then dividing by that increased exponent. So it's exactly the opposite of the derivative which said drop the exponent first and then decrease the exponent by 1 unit. And you'll find that that's true throughout this entire list. True to its name, the derivative and the antiderivative are exact opposites. So if the derivative of the exponential is the exponential, then the antiderivative is the exponential as well. Now, the natural log function, when you take its derivative, becomes 1 over x. The antiderivative is a little bit more complicated and typically not worth memorizing. However, if we start with the function 1 over x and we want to find the antiderivative of that, the antiderivative of 1 over x is the natural log absolute value of x. So what we can see is that the antiderivative of 1 over x is backwards to the relationship of the derivative of natural log of x. Notice that when it comes to integration, we do have to deal with 1 over x separately than x to the other powers, because 1 over x corresponds to an exponent of n equals minus 1, which means that n plus 1 would be equal to 0. And therefore, this formula would be invalid for that one specific exponent because you cannot divide by 0. Now moving on to sine and cosine, if I take the derivative of sine, the result is negative. If I take the derivative of cosine, the result is negative sine. If I take the derivative of sine, the result is cosine. And the antiderivatives are backward. If I take the antiderivative of cosine, the result is sine. If I take the antiderivative of sine, the result is negative cos. So absolutely at a minimum, you should have these formulas memorized, all 6 of them. That is the basic expectation for memorization involving derivatives and antiderivatives. Now, there's a very useful idea and very useful word in mathematics, which is called a linear combination. A linear combination describes a combination that was accomplished using just addition, subtraction, and constant multiples. Just addition, just subtraction, and just constants multiplied. And the reason why linear combinations are so important in specifically derivative and integral calculus is that linear combinations of toolkit functions are extremely easy to deal with because of the sum rule, the difference rule, and the constant multiple rules for derivatives and integrals. So, for example, if I gave you the function 3x cubed plus 2e to the x plus 4 sine of x, this one is a linear combination of toolkit functions. Because it is obtained by adding together constants times the toolkit functions that are in this list, which means it's very, very easy to find the derivative of this function, and it's very, very easy to find the antiderivative of this function. The derivative could just be found by copy-pasting the constants and the plus signs and finding the derivatives of just the toolkit functions in between. And the same thing is true for the antiderivative. I could just copy paste all the constants and all the plus signs and simply find the antiderivative of all the functions in between. Note that I'm not including the plus c here because I'm not trying to write down the indefinite integral. I'm just writing down one specific antiderivative at the moment. Although if you were trying to write down the indefinite integral, you would include a plus c at the back. Now, by contrast, if I gave you a different function that was combined in a different way, for example, if I gave us the function, let's say x e to the x, this is two toolkit functions that have been combined using multiplication. And so it would be a combination of toolkit functions, but not a linear one. Which means in general, it's going to be much harder to find a derivative or an integral of this function. The derivative would have to be found using product rule, and the antiderivative would have to be found using integration by parts in this case. The same thing is true about the function e to the x squared. This is a combination of toolkit functions, but the combination has been achieved via composition. So that means that the derivative of this function would need to be found using the chain rule, and the antiderivative of this function is actually impossible to find. This function is, believe it or not, too complicated, and you cannot find an antiderivative for this function. So that's why linear combinations are so important. A linear combination of functions, specifically a linear combination of toolkit functions, has a derivative and an antiderivative that are both extremely simple to find using just the sum rule, the difference rule, and the constant multiple rule. But when you get into the territory of dealing with products or division or composition, that's when derivatives and integrals tend to be much more difficult to find or even sometimes impossible to find. For example, there are only sort of two special varieties of products that are possible to integrate. Products that can be integrated using substitution and products that can be integrated using integration by parts. For integrals using substitution, the format that you're looking for in your integrand is something like this. An outer function that has some inner function plugged into it, and then elsewhere in the product, the derivative of that inner function. When you're applying method of substitution to a problem, your goal is to let a single variable u replace the quantity g of x, so that the du can replace the quantity g prime of x dx. And therefore, this entire integral can be turned into one in terms of u alone. Something ideally that is much simpler in the variable u than it was in the variable x. To give you an example of a problem that I would definitely approach using u substitution, if someone asked me for the indefinite integral of x squared times the square root of x cubed plus 2 dx, I see I have an inner function here, x cubed plus 2, on the inside of this square root. And I have something very closely resembling this inner function's derivative outside multiplied by that square root. So I would let u be equal to this inner function, so that du was 3 times x squared dx, or in other words, this x squared dx that I have in my problem is equivalent to 1/3 du. So if I take my integral and I transform that square root of x cubed plus 2 into a square root of u, and if I transform this x squared dx into 1/3 du, now this is a linear combination of toolkit functions which I can integrate easily using just the constant multiple rule and the power rule for integrals. Increasing that power by 1 unit, dividing by that increased power, giving me 2/9 u to the 3/2 plus c, or putting back what u was originally equal to, this would become 2/9 quantity x cubed plus 2 to the power 3/2 plus c. So substitution is meant to help us to integrate special nonlinear combinations of specifically this format, f prime of g of x times g prime of x. In other words, the kind of thing that you would get when you apply the chain rule from calculus 1 to a function. Substitution is basically just chain rule backward. Now, the other special product that we learned how to solve in Calculus 2 were products that could be approached via a method which was called integration by parts. And integration by parts said that if you have the integral of a product of the format, let's say v times u prime, then that could be rewritten as v times u minus the integral of v prime times u. So the kind of setup that you would see if you are thinking about using integration by parts is a product where one piece of the product specifically the piece here called v, becomes simpler when you take its derivative, and the other piece of the product here called u prime has an antiderivative which is not too complicated or hard to find. So to give you an example of a situation where I would definitely be using integration by parts, let me give you, for example, the integral of x times e to the 3x dx. When I look at this example, I would be thinking of x as the function, which becomes simpler when you take its derivative, because when you take the derivative of x, it just becomes a constant. So that's really, really simple. And then the other piece of this product here, e to the x, has an antiderivative that is not much more complicated than the original function. Using substitution, the antiderivative is 1/3 e to the 2x. So then if I put that information into the right half of the integration by parts formula, I find that this integral is equal to x times u, or I should say v times u, which in this situation is x times 1/3 e to the x, minus the integral of v prime times u. Now this integral in the back is much easier to solve than the original integral because this integral in the back does not contain a product. It just contains a constant multiple. So if I integrate that using the constant multiple rule and using a simple substitution for this 3x, I get this result. So those two rules, substitution and integration by parts, could help you to integrate nonlinear combinations, certain products in certain special cases. However, most of the time, the functions that you're integrating do not have an antiderivative that you can find. I'll give you some frustratingly simple examples. The integral of e to the x squared. You're done. There's nothing that you can't proceed from here. There is no rule. There is no process that's going to help you with this. This is not a linear combination of toolkit functions. This isn't a product where substitution can be applied. This is not a product where integration by parts can be applied. So this is an integral where there is no antiderivative that can be found. I'll give you another frustratingly simple example. This one right here, 1 plus x cubed square rooted. This is another situation where you're really going to be hard pressed to find an antiderivative if one exists at all. To give you another frustratingly simple example of a function that really doesn't have an antiderivative, integral of, let me say, x times cosine x cubed dx. It's over for us, right? We don't have an antiderivative method that applies to this particular product. If it was cosine of x squared, we would be able to use u substitution. If it was an x squared out here in the front, we would be able to use u substitution. If it was x outside and x inside, we would be able to use integration by parts. But anything else besides those three really lucky circumstances, we're just completely stuck and we cannot proceed. So I really want you to understand how lucky you actually have to be in order to have an antiderivative, have an integral where you can actually find an antiderivative. All the functions that you encountered in Calculus 2 are kind of manufactured and carefully selected by your teacher to be lucky, but most functions have no antiderivative. That's why at the end of the day, your most faithful and reliable friend is the Riemann sum estimate from a couple of lessons ago. Most integrals must be estimated using some kind of Riemann sum. So Riemann sum estimates are important, and Riemann sum estimates represent the majority of what you're actually going to be doing with integrals when you leave school and are doing integrals in the real world for actual career applications. So don't abandon Riemann sums. They're very, very important.